So yes, we continue with the topic general trends in the properties of transition elements, and we'll be doing a different property today. Now, as usual, this is a periodic table and I'm not going to bore you every day with all the details. You know what you need to know. This is the portion that we are studying. This is the D block of the modern periodic table. And today's property is ionization enthalpies, right? We'll be talking about the ionization energies of D block elements. Primarily, we'll discuss about the ionization energies of 3D series. Now, first things first, let's just revise what this ionization energy is. आपने 11th class में पढ़ा है. It's the energy required to expel the most loosely bound electron from an isolated gaseous atom, right? The first ionization energy is the energy required to remove the first electron. Then if we remove the second electron, it's called the second ionization energy. If we remove the third electron, it's the third ionization energy, and that is how we have successive ionization energies of an atom. Now let's see what are the important points which we need to learn and remember about D block elements. The first ionization energy required to expel the first loosely bound electron of D block elements is more than S block elements and less than those of P block elements. Somewhere right in the beginning of this topic, I told you जो transit of properties होगा हमेशा from S to P that happens through D. So in most of the properties, the values of D block elements are between the values of S and P. Like that trend, value of the ionization energies of these D block elements, as is written here, is more than those of S block elements and less than those of P block. So it lies in between S and P as expected. Now ionization energy gradually increases. It increases, but the increase is gradual with increase in atomic number along a given series. Why? Because a series is a part of the period, and period की trend यही होती है. From left to right in a period, ionization energy increases because from left to right in a period, the dominant effect out of all the possible effects is the increase in nuclear charge. Increase in nuclear charge इतना हो जाता है, electron cloud contract हो जाता है with every successive atom. That is why it becomes difficult to remove that most loosely bound electron. That is what is written here. Ionization energy increases gradually with increase in atomic number along a series. However, there are some irregularities. I made a table here. If we speak about the ionization enthalpies of the first transition series, and these are the elements: scandium, titanium, vanadium, chromium, manganese, iron, cobalt, nickel, copper and zinc. If you take a look at the first ionization energy, there is just one irregularity. Gradual increase है, and इस increase में सिर्फ यहाँ पे irregularity है. 758 के बाद nickel is 736. Otherwise, it's a gradual increase from left to right, from scandium to zinc. However, the irregularities are more evident when we speak about the second ionization energy and the third ionization energy. The energy required to expel the second most loosely bound electron and the energy required to expel the third most loosely bound electron. As you can see in the values, बहुत irregularities. Here it increases, then it increases, then it increases, then there is a sudden decrease. We'll see why that happens. Now first, the reason of irregularity क्या है? The reason is very important to remember. What happens is कि जब आप किसी इस 3D series के element से first electron निकालते हो, now it is in the +1 oxidation state. After that, what happens? There is a reorganization of the energy in 4s and 3D. The general trend is that आपका जो upper principle है, that says कि पहले इलेक्ट्रॉन 4s में जाएगा, उसके बाद 3D में, because energy of 4s is lower than 3D. But once the first electron is removed and the 3D element is in +1 oxidation state, the relative energies of 4s and 3D undergo a change. Their relative relationship alters, because of which there is reorganization, and the energy involved in that reorganization is called as the reorganization energy. Now, consequent to this reorganization energy, what happens exchange of electrons starts from one orbital to another, and there's a release of exchange energy. There's a release of exchange energy, and the value of the exchange energy will increase with increase in the number of electrons. So precisely to summarize it, a lot of things are happening. Once the first electron has been removed and the transition element is in +1 oxidation state, a lot of things happen there, because of which in the second ionization energy and in the third ionization energy we observe a lot of irregularities, right? I'm sorry for this little background noise. I think this is what happens when we work from home. Now again, moving to the next point, I would like to speak a little bit more about this point. I think we lost it somewhere in between. The trend is irregular as far as the ionization energies second and third are concerned. Why? Because a lot is happening in monovalent positive 3D ions, right? The next point is very simple. The first ionization energies of zinc, cadmium and mercury are very high because their configuration is, they are stable configurations. They are fully filled orbitals. Zinc is 3d10, 4s2, cadmium is 4d10, mercury is 5d10. It is very, very difficult to alter this stable configuration to remove the electron. Thus, even if we have to, the energy required is very high. The next point is very important. ये जो order इसमें दिया हुआ है, as far as the objectives are concerned, concerning that, these two things are very, very important. In the second ionization energy, what you observe here is that vanadium is less than chromium, but chromium is greater than manganese. In the second one here, यहाँ पे chromium तक trend ठीक है. Vanadium से ज़्यादा chromium की ionization energy है, as should be the case, but then manganese की कम हो रही है. So that this is the order: vanadium less than chromium, but chromium is greater than manganese. We'll study what the reasons are, and the same thing happens here. Nickel less than copper, but copper greater than zinc. If you remember the electronic configuration of these, you know that chromium is 3d5 4s1, right? Copper is 3d10 4s1. So after losing the first electron, what is left behind? Chromium is left behind with the stable configuration of 3d5, 4s is 0 now, and copper is left behind with a stable configuration of 3d10. Now it is obviously very, very difficult to disturb that stable configuration. That is why the second ionization energy of chromium is very high and that of copper is very high than the previous element. However, when we go to manganese, manganese will now, after losing the second electron, it will acquire that stable configuration. So it is easier for manganese to lose the second electron. Similarly, for zinc, it is easier to lose the second electron because after losing both the 4s electrons, it will acquire its only oxidation state, which is +2. That is why this order, right? Vanadium is less than chromium, which is normal, but chromium is greater than manganese because chromium की second electron निकालने से stable configuration disturb होगी, and manganese second electron lose करने से acquire करेगा stable configuration. Same is the reason for this order between nickel, copper and zinc. Now after that, ionization energy third. Let's speak about the third ionization energy of manganese. Now as you know, second ionization energy of manganese कम क्यों है? Because it will be losing the second electron and acquiring the stable configuration. Now जब आप third निकालोगे, look at this, it is very, very high. अब जब आप third निकालने की कोशिश करोगे, it has already acquired stable configuration after losing the second electron. Now it is 3d5. And 3d5 को डिस्टर्ब करने के लिए, तीसरा इलेक्ट्रॉन निकालने के लिए, the energy required will be very, very high. That is why जब भी आप values देखोगे, इस value में जो, इस table में जो irregularities है, all of those irregularities have a reason, and the reason of this exceptionally high third ionization energy of manganese is that the removal of third electron is to be done from the stable half-filled orbitals, which is very difficult. Contrary to that, look at this point. The third ionization energy of iron is very small, See, everything depends on the electronic arrangement. आप जब second electron remove कर रहे हो iron का, it comes into the Fe2+ state. It hasn't acquired stable configuration yet. It will acquire stable configuration when it loses the third electron. That is why in between manganese and cobalt, you can see दोनों से कम है ionization energy, third ionization energy iron की. Because after losing that third electron, it will acquire stable electronic configuration. Thus, it is very easy to remove that third electron. The purpose of all of these points is to explain these very evident irregularities in the second and the third ionization energies of the elements of 3D series. Right? Next, you will see very high values of IE3, the third ionization energies of copper, nickel and zinc. Let's take a look. Copper, nickel and zinc. तीनों की third ionization energy. The energy required to remove the third electron is very high, which explains why these metals, copper, nickel and zinc, exist in +2 oxidation state. Up to +2 oxidation state only they have their oxidation states. That is their maximum oxidation state. They do not lose the third electron. This point is also very important. I have a graph here, and in this graph, this dotted line is the plot of the 3D series. This slightly broken line is the plot of the 4D series, and this solid plot is the plot of 5D series. The first thing you observe in this is that ionization energies of the elements of 5D series are very high as compared to the ionization energies of the elements of 3D series and 4D series. What is the reason? The reason is given here. Ionization energies of 5D elements are higher as compared to the elements of 3D and 4D series because of the poor shielding effect of 4f electrons. ये 4f कहाँ से आए? This is your 5D. 5D में first element is lanthanum. After that there are lanthanides जिनमें filling होती है 4f की. So यहाँ पे 4f fill हो चुका है. After that 5D starts filling. Now from left to right, the dominant effect in a period is nuclear charge. दूसरा effect जो होता है, the electrons, अंदर वाले electrons, they can shield the outermost electrons from that nuclear charge. However, यहाँ incoming electron कहाँ गया? 4f में. And 4f electrons have a poor shielding effect. They are not able to shield the outermost shell के जो electrons है उनको from the nuclear charge, as a result of which effective nuclear charge increases. The effect of nuclear charge felt by the outermost electrons is higher. That is why the size contracts further, and when the size contracts further, it is even more difficult to expel the outermost electron. We are talking about the first ionization energy only. पहला इलेक्ट्रॉन ही निकालना 5D से मुश्किल है because उनकी जो effective nuclear charge है that is greater than that of the elements of 3D and 4D because of the poor shielding of 4f electrons. Now in a given series, the difference in the ionization energies between any two successive elements is very small. In a given series, अगर आप move कर रहे हो from scandium to titanium, there is an increase, but it is not a massive increase. The increase is very small. The difference between the two successive values of the two successive elements is small. Compared to what? Compared to the S block elements. S block element में अच्छा खासा difference होता है. This is a graph again. You have the plots and you can see the trend in each series. And then the very important point that we have to remember from this plot is that the ionization energy, first ionization energy of the elements of 5D series is much higher than those of the 3D series and the 4D series. I have added a slide of one more property in this presentation because the description of this property wasn't much. It is just one slide, so I thought that we'll be doing this property also in this presentation only. The property is density. You know what density is. Density is directly proportional to mass and it is inversely proportional to volume. So if we know what happens to mass and what happens to volume, we can know what will be the trend of the density. I've highlighted here that in a series from left to right, density increases, right? in this D block of the periodic table, if we move from left to right in any series, density will increase. What is the reason? Because from left to right in a series, atomic radius decreases. We know this. Atomic radius जब decrease हो जाता है due to the increase in nuclear charge, it has an effect on atomic volume. Decrease in atomic radius leads to decrease in atomic volume, while atomic mass increases because your adding atomic number is increasing from left to right and atomic mass goes on increasing. So these two things happen. From left to right in a series, atomic volume decreases due to decrease in atomic radius, while the atomic mass keeps on increasing. Consequent to both of these things, from left to right in a series, density increases. The values of the densities of the elements of 3D series are given here in the small table. We can see the trend. It is increasing constantly with a few irregularities here and there, I guess, but otherwise it is increasing, right? In fact, there is no irregularity. The only irregularity there is that of zinc, which we know that zinc, cadmium and mercury, they behave differently as compared to the other D block elements. Now, two important points to remember here is that in the whole D block, iridium has highest density. Iridium, I guess, it's an element present in 5D series, I believe. Yes, in 5D series here, after osmium, we have iridium atomic number 77. And pure D block mein iridium 77 has the highest density. What is the value? 22.61 gram per cubic centimeter. And scandium has the lowest density. I haven't written the value here because the value is already given in the table. 3.43 is the lowest value of a D block element, and that element is scandium, right?